Section 4.6 is Newton's method. Here is page 1. So Newton's method is an algorithm that uses tangent lines to approximate the roots of a function. So remember, roots are sometimes referred to as solutions, the zeros, essentially the x-intercept of a function. So what ends up happening, and in terms of an algorithm, think of it as an iterative process. So we're going to make some initial guess as to what the zero of a function would be. And this is your starting point, your x1. So I have a graph below, and we're going to start with x equals 5, but you could have picked anything. So it's hard to see, but I've got this blue function. I just did a horrible job of drawing it, but hopefully you can see it for the most part. And I happen to pick x1 to be the value of 5, but I could have picked 2, I could have picked 8, it doesn't matter. But as soon as you pick some x1 value, you want to find the output. The output is going to be on the graph. So I went down to my graph and I made this point. Now I want the tangent line at that point. So if x1 is my purple value, I drew a purple tangent line to my graph to get my tangent line for x1. You want to draw your tangent line such that it goes through the x-axis. So like if I'd only drawn it this short, that's not going to help me. I needed to come all the way over here so that I crossed the x-axis. And I went a little beyond just for clarity. But as soon as you find that point on the x-axis, your x-intercept, that's your new x value. So now my x2, instead of being 5, it looks like it's, 12.5. Where does this hit my graph? Well, remember my graph it's hard to see, but had spun up. So I need to come up until I've got my output for x2. And because I used orange, I now drew an orange tangent line, which is the tangent line for that. Remember, I needed my tangent line to come far enough down to cross the x-axis. So here's this green point where I've crossed the x-axis that I'm now calling my x3. When I go to find the graph, I don't have very far to go. I go up again this time. Notice our answer is somewhere in between 9 and 10. And now, I don't know, it looks like I'm at 9.5, 9.6. I go up to the graph. I draw that green tangent line, and it's hard to see. Let's see how good I can do zooming in. But hopefully it's clear that that green tangent line is almost right on top of where the graph is at the x-intercept point, the solution. So that's our process. So now let's go ahead and figure out the formula for what we did. We picked any x value, but we focused on what the output was, where it hit the graph, and then we made a tangent line. And so our tangent line has a slope of f prime based on whatever that input was, right? The slope of the tangent line is the derivative of the function. So tangent lines are linear. So I took my linear equation and I said I had an input of x1. So I put, x to the n, whatever guess I'm on. And it had an output of f to the x to the n value. We know that the slope is the derivative at that same point. And I'm stuck with y and x. But remember, we want a solution. We want to know when we're on this x-axis. So we want the height to be 0. So really, we can just get rid of that. And now x is the true solution. So what we do is we divide both sides by f prime so that I don't have f prime on the right side. And I'm going to go ahead and add the opposite of x to the n to the left side. So I have this formula right here that says you're just going to keep doing this as n keeps increasing to find the true solution. If I haven't had you watch this video, definitely watch it. It explains it visually much better than what I have drawn above. Now, in reality, if you know how to program, go ahead and write some code for this. Use a spreadsheet where you write formulas, or even go ahead and use your calculator where you can bring up the last entry of your calculator, and you're just going to keep swapping the output value. Well, let me rephrase that. The input value you get into your function.